what we have is some data that we've seen before. So let me see if I can blow this up a little bit so everybody can see it, although you should be able to see it on your own monitors. We have the date. So we have production data basically. So a date, and we converted that to time. So January 1964, we call that t is equal to 0. We've put the time in hours because some of our equations are built to do it in hours. The unit conversions are already built in, so we've put that in hours, and we've calculated that here. The pressure is given. Again, that's most likely from pressure gauges and wells, maybe an average of different wells if there's more than one. And then we have the oil, gas, and water production as a function of time. And then we have the formation volume factor of the oil, which is a function of pressure, but pressure doesn't change much, so not surprisingly, BO doesn't change much either. So BO is a little bit greater than 1, as is usually the case, right? So it's about 1.078. Other information that might be useful. By the way, I should say that please turn on your videos. I'm going to be calling on you, and you know, I may be calling on all of you, but I will probably most likely call on the people first that don't have their videos on. So I'm trying to get as much engagement as possible. So the initial pressure is 2532, and you could see that in the table as well because the pressure was 2532 in 1964. The temperature of the reservoir is given. The bubble point is 737 psi. So Andrew says that this is an undersaturated reservoir, meaning that no gas is present at reservoir conditions. And that's exactly true. So the fact that if we were below the bubble point, we would have gas as well, but we only have an oleic phase at reservoir conditions. Now that doesn't mean that when we bring it up to the surface we won't have gas. In fact, we do, and that's why we produce gas. So those are different. Okay, so the original oil in place, that's N, is given to us. That was probably measured by volumetrics using a contour map that a geologist provided. Initial solution gas ratio, formation volume factors, formation volume factor of the bubble point, initial water saturation. All this may or may not be needed. We'll see. Compressibilities of the formation water are given, as well as the porosity, permeability, and thickness of the reservoir. The thickness of the reservoir was given as 31.8. Again, that's probably measured from a geologist in a map that was provided. We don't have a great idea of what the thickness of the aquifer is. So for now, we're just going to assume that it's the same as the reservoir. We don't have any reason to think otherwise at this point. The volume of the reservoir is given in acre feet, 73,590. The angle is 360 degrees. That means that there's no ceiling faults or anything, so it's a completely radial reservoir. RA is unknown, okay, at least for now. And the water and oil viscosity are given. Okay, so I'm going to give you all about 5 minutes or so, and I want you to calculate the F factor, the area of the reservoir, and by the way, we did all this, or a lot of it, because we did the same example for a small pot aquifer 2 weeks ago, exactly 2 weeks ago, so it was that Friday. So if you need to, you can go back and remind how to do that. But area of the reservoir, the radius of the reservoir in feet. RED, actually we won't be able to calculate that yet because we don't know RA. So we'll just leave that blank. Calculate U. So we have a U is given here. So this is on slide 13 of your PowerPoint notes, and U is given here. And I'm going to repeat something I have in the past. This 1.19 is a conversion factor. It's actually 2 pi times a conversion factor. So as long as you use compressibility and inverse PSI, thickness in feet, and radius in feet, you don't need to do any conversion to get this into barrels because that's what the 1.19 is. In fact, it's exactly 2 pi divided by 5.61. There's 5.61 cubic feet in a barrel. Likewise, the dimensionless time, it doesn't need unit conversions as long as you use the right oil field units as I've listed here. So I saw that mistake in office hours for some of you when you're trying to calculate TD. But I'm going to give you about 5 minutes and calculate everything but RED and this capital CT. We don't need that. So F, area of the reservoir, RE, and U. So B30 divided by 360 is 1. Okay, now, you know, and if I wanted to change the angle there, you know, then you could do that. So it's a good idea to actually put in the formula rather than just type 1, because if we change up the problem somehow, then it would automatically change everything. So what about the area of the reservoir? 7350 at 590 divided by the thickness, 31.8. Then we get 2314.2 acres. Okay. Now the next step is to calculate the reservoir radius in feet. Okay, so if you remember, if you go to slide, what is this, 4, calculate the reservoir radius is equal to the area of the reservoir divided by pi f and take the square root of that. So it's going to be the area. We can do the area there divided by pi, 3.14159, and then let's see, what else do I need? Oh, it's going to be the square root of that. But I need to convert acres to square feet. So there's what, 43,560 square feet an acre, if I remember correctly. And well, I think I might have been a little bit off. Well, maybe that's the problem. And I should have put the F in there as well, right? Because times F, which is 1. There you go. So I got 5,664.5 feet. Hopefully that's what you all got. We did do this problem a couple weeks ago and we got the same thing. So I'm going to go ahead and give you what the aquifer radius is at this point. So we're going to say it's 275,000 feet. So it's clearly much bigger than the reservoir radius. And if we do the dimensionless radius, it's going to be the aquifer radius. So that's B31 divided by our reservoir radius, which is B38, and I get 48.5. So the aquifer radius is almost 50 times bigger than the reservoir radius. I suspect that this will be infinite acting flow at most times. Maybe if you go to long enough times, it wouldn't be. And then what about U? So the formula for U was given on slide, well, it was given a couple of places. It was given on slide 18. I think it might have been also on 13. And it says 1.19 F times porosity times total compressibility times thickness times the reservoir radius squared. So maybe I'm going a little fast. So U is 1.119, and then we've got FVCT. So I can go into here and I can put times F, which was B36, times porosity, which is 0.177, times the total compressibility. So I'm going to put a parentheses and say that that's going to be the water plus the formation compressibility. So I'll close that. Times, what else was on there? That was the thickness times the radius squared. So thickness, and oh, we need to be careful here. What is this going to be? I think that is going to be the thickness of the aquifer. So I'm going to do B28. Oh, well, times B28. and then I'm going to multiply by the reservoir radius squared. Okay, so I got 1414.68. Is that what you all got? I think we did this 2 weeks ago and we got the same thing for you. So you should get 1414.68. And remember, that's going to give us the answer in reservoir barrels per PSI. We didn't need to do any unit conversions there because we used all the right units. They were actually in cubic feet, but when we multiply by the 1.19, that has the 5.61 built into that coefficient. So now what we're going to do is we've calculated these variables, we got all this other stuff. We're going to go to the Fetkovich tab, and we are going to try to compute some of these things here. Okay, so I'm going to blow this up. And what I've done, I've sort of made some of this easy so that it's easier, make it a little bit faster for us. I've put in all the data. This was given to us. This is just copied and pasted from the data. And then we have our table here, which is similar to the table I proposed here. So what I proposed is that we've got our time and our pressure, and then we calculate these different things. So what this column is Pn bar. P stands for pressure, bar usually indicates an average, and the subscript n indicates the time n. Okay, and at the first time, the average pressure is just going to be equal to the initial pressure. And then at future times, that average is going to be the current pressure plus the last pressure divided by 2. Right? So the idea is that pressure is changing over that period, so we're going to use an average over there. So it's 1/2 Pi plus P1, 1/2 P1 plus P2, 1/2 P2 plus P3, etc. Then I have a column which is the average aquifer pressure minus the reservoir pressure. Okay. Now initially the aquifer pressure and the reservoir pressure will be the same. They'll be equal to Pi, so that's 0. This column is going to be delta WE, which is the incremental water that gets influxed into the reservoir. Obviously that's 0 at time 0. We haven't had any water come in. And the cumulative, which is what we had at the previous time level plus any new incremental, so that's still 0. And then the average aquifer pressure at the current time level. So PA stands for aquifer pressure, the bar indicates some sort of average, and N indicates the time. That's equal to PI at that first time level. At the second time level, PAN minus PN is going to be this column, PI, minus P1 bar, which is going to be already calculated here. Delta WE, now that's the tough formula. Okay, and I think I made it easy for you today. I think I plugged in the formula for you, just because I know that can be tedious and that might be a few minutes and then maybe you made a mistake and stuff like that. So I think I put the formula for you in Excel, but the formula that we derived the last 2 class periods was that the incremental water influx is equal to WEI, which is a constant of the aquifer, divided by the initial pressure, times the initial pressure minus, or I should say, times this delta P here, which is given in this column. All of that times 1 minus E to a productivity index J times the initial pressure divided by WEI times a delta T. So that's the most complicated thing to calculate, but I put that formula in there for you. And then the cumulative water is equal to the incremental water plus whatever the cumulative was at the last time level. And then we can calculate a new average aquifer pressure, which is the initial pressure, times 1 minus WE1, which is what we calculated here, divided by WEI. It's clear from this that we're going to need to calculate WEI and J, which were given, let's see if I can, oh, no. It was right there, right? So we're going to need to calculate WEI and J. WEI is given as the initial pressure times the total compressibility times pi times the aquifer radius squared minus the reservoir radius squared times the thickness of the aquifer times the porosity times F divided by 5.614. So again, we're putting radius and thickness in feet, and this 5.61 will automatically convert that to barrels. And then J is this constant, which is a conversion factor, times K times the aquifer thickness times F divided by the viscosity times the natural log of the aquifer radius divided by the reservoir radius minus 0.75. So that would be a little tedious to put in, but I did that for you. So if you go to this slide where we have Fetkovich, I wrote down the equations again, just so that you can see them, and I had the formulas in there. So those, you should get these same numbers provided that you did the calculations right a few minutes ago. So I get WEI is 4.220 e to the 9th reservoir barrels, and I get J is equal to 81.731 reservoir barrels per day per PSI. So if you're getting a little bit different answer, or a lot different answer, then maybe some things in your data were wrong, especially the calculated variables. So maybe double check that. Okay. And I'll give you 60 seconds to fix that, and if you can't, then I guess for now you could just plug in these numbers in these two cells and it'll suffice. Again, here's what I get for WEI, 4.220 e to the 9th, and J is equal to 81.731. If you absolutely have to, I suppose you could just type those in, although that's not ideal, and I encourage you to go back and fix that. So the next thing is we want to calculate these other variables in the table. So the average reservoir pressure, and I didn't put the bar on top of here, it's just a little tricky to do in Excel, but this is the average reservoir pressure. It's going to be equal to the initial reservoir pressure, which is 2532 at first. This is 0, we know that. Delta WEN, that's of course 0. WE is 0, and PAN is again equal to the pressure right there. So that was pretty straightforward. Okay, and we saw that in the table in the PowerPoint notes. It's the next column and all the following, I mean, it's the next row and all of the following rows that are a little bit more complicated. So the first thing what we need to do is calculate the average reservoir pressure on October 1964. And then what is PN?
2503.
That's right. So it's C4 plus C5. And then, of course, divided by 2, and that gives me an average pressure. So I get 2517.5. And then I want PAN minus PN. So what would that be? This is PA, the aquifer pressure at the previous time level, and that is column H. So what we really want is H4 minus PN, which is D5. And that's important because even though it was 2532 in 3 different places, in the future times that won't be the case. And we're gonna drag and drop. So do you understand why that's it now? Hopefully. So we have that. And then, because I put the formula already in there, delta WEN already appears. And we calculated that using this formula here. So this formula I have boxed, delta WEN is equal to WEI, which we've calculated, divided by the initial pressure, times PAN minus 1 minus PN, which we just calculated in the previous column, 1 minus e to the j, we've calculated j, pi, WEI, we know all that, times delta t, and we got to be really careful with our delta t, and that delta t is 6576 minus 0. So it's the incremental time, so that's the delta t. So hopefully you got that. And then WE is just going to be equal to what WE was at the previous time level. So I put G4 plus delta WE, which is this F5. And of course that's the same, right? Because I had 0 before, so if you add the incremental amount to 0, you're going to get the incremental amount again. And then I'll give you about 2 minutes to calculate this PA. It's going to be equal to the initial pressure, which is C4, times 1 minus WEN, which is going to be G5, divided by WEI, which is going to be B16. That sounds like what you told me you got, 2531.81. So hopefully you got that. Now I want everybody to be really careful because let me show you again what I did. So it was PI times 1 minus WEN over WEI. So PI is 2532, WEI is given by B16, and the WEN was this G5. Okay, but we're going to repeat this calculation over again, and of course we don't want to have to go through typing that all over again. So PI never changes, so this C4 should be fixed. So if you are not really good with Excel, maybe you don't know this yet, but if you put $C, $4, then when I copy that formula, it will keep $C, $4. And the same thing goes for B16, WEI. I don't want it to change. So I put $B, $16. But I do not, I'm going to repeat, I do not put the dollar signs around G5 because G5 is going to be changing each time. So I want to use G5, G6, G7, etc. So I'm going to do that. And it doesn't change the answer here, but it would in subsequent rows. And then we can highlight row 5. It's D5 through H5. And we can drag and drop. So I'm going to delete that again, so show you again what I did. Okay, we were here. You should have gotten these things on the row. You got to be really careful with how you calculate PAN and in column H. You want to use $C, $4 and $B, $16 so that when we copy it, it keeps those values because PI and WEI never change. But we don't put dollar signs around G5 because that will change. And what I did is I highlighted these. I go into the bottom right corner. You have a little black cross there and you drag and drop and you get your solution there. And that's it. That's our whole solution to the Fetkovich method. That is a lot easier than the VEH method. And if you haven't noticed that yet, you will on your upcoming homework. And what it really is it's this approximation that the pressure is dropping by a percentage equal to basically the water that has encroached compared to the maximum approachable water. So when nothing's come in, then P is still equal to PI, and if you were to maybe encroach everything, it would go all the way down to 0. We don't have much time left. We've got 7 minutes, so maybe I'll go through this next part myself. But I will say that the other video I referenced to is kind of goes through this in more detail. So if you need to, you can do that. And I'm going to do one other thing here. I'm going to try to calculate WE from a material balance, and I'll try to see if I can explain how I did this. So these columns here, A through G, were given to us in the data. This is our production data. Date, time, pressure, oil produced, gas produced, water produced, and the formation volume factor there. What we're going to do is we're going to calculate F. F is the production of fluids. And this is an undersaturated reservoir, so it's pretty straightforward. It is the oil produced times the formation volume factor of oil plus the water produced times the formation volume factor of water, and I think the water formation volume factor was 1.02. So that's what we get for F. I won't go through EOWF, but you're all familiar with that. It's a PVT property, and the equations in the equation sheet. And then what I'm going to do is I'm going to calculate WE from a material balance. So let me see if I go here. How are we going to do that? Well, the material balance is this equation right here. So NEOWF plus WE is equal to F. And again, we calculated F already. So WE is simply F minus NEOWF. And so if I go back to this here, and that's how I calculated K. And you can even see I put I4 minus J4 times the calculation in there. So that was the WE is equal to F minus EOWF times the original oil in place. The original oil in place was given here, OOIP is 48.75 million stock tank barrels. So if I go back, this is the water influx from the material balance equation. And you know, we only had a short time today. I really encourage you to do all this on your own. It'll be helpful in your next homework. It'll be helpful in your exam. I do have a separate video which might go into a little bit more detail, which will be helpful, but I would work through this on your own. But the key point in here is that now I've got at least actually three different ways to calculate the cumulative water influx with time. One of them is the material balance equation. Another is the Fetkovich method, which we did the first part of this class. And the last is the VEH solution, which I did in part earlier this week or last Friday. And so I made a little table where I compared those. So I did this comparison where I have the material balance. I just copied and pasted from that tab, the VEH method, and the Fetkovich method. And if I make a plot of that, if I make WE in reservoir barrels versus time, you see what my plot is here. Now the Fetkovich and the VEH match almost perfectly. They match almost perfectly, which is what I told you what would happen. I said the VEH is more accurate, but it's so much more tedious, and the Fetkovich is almost as accurate, and it's a lot easier. And they match pretty good. But from the material balance, we get a very different answer. So something seems wrong. Okay, it could be with my material balance equation, but I trust my data, and I've double checked my geologist, and the original oil in place and the bulk volume and stuff were correct. So I don't think it's there. That means that something is wrong with our VEH and Fetkovich method. And I don't think it's my calculation. I mean, for one, the two match each other. So I would have had to make an error in my calculations in two different places, and by coincidence I would have gotten the same thing. And also I've double checked it a few times. So what could be wrong? Does anybody have any ideas? We got 1 minute. A lot of this depends on knowing my aquifer properties. My aquifer permeability, porosity, thickness, compressibility, those kinds of things. And if you remember at the very beginning of the class, I said I don't really know my aquifer thickness. I'm going to guess that it's 31.8. Okay, does that sound familiar? All the way back at the beginning of class. And so I can change these. What if I put 40? I go back and look at my summary here. Maybe it's a little bit better. And I can keep on playing with this, but if I put in 71.3, it's almost identical. Okay, so what does that tell me? That tells me that, you know, maybe my aquifer, in all likelihood, my aquifer thickness was incorrect. It's actually much bigger than the reservoir thickness. So that's what we call history matching. We match the data to our model in such a way that we change variables in order to get it right. So now we know what the aquifer thickness is, right? Maybe the other alternative would have been to drill a brand new well and do some logging to figure out the thickness, but that wouldn't have been very economical at all, right? And your boss would have laughed you out of their room. So it is 11:50, but are there any final questions about this?
So did you just pick the height of, because there's a lot of other parameters, was height just the parameter that
yeah, that's a really good question. So the question is basically, why did I decide to vary the thickness rather than some of the other parameters? It could have easily been some of the other parameters. I happen to know that that was the one that we were least confident in. So things like viscosity, well, we have a pretty good idea of that. Compressibility, we're not going to be far off on. Thickness is, it could have been one of those other ones, but thickness is the one that we had the least amount of confidence in.